Hey, what's up everyone? Jason Turley here, back with more PicoCTF, and today I just wanted to showcase my solution for pi time 2. In the previous video, we knocked out pi time number 1. These are both binary exploitation challenges that will have us circumvent a mitigation called pi, position independent executable, meaning the base address of the binary can be loaded at different spots every single time you run it. If you're familiar with ASLR, for randomization of library code, this is essentially the same thing, but for a binary. So we can read the challenge description. Can you try to get the flag? I'm not revealing anything anymore. And then we get this netcat connection line. But before we do that, before we try connecting to the server, we do have access to the source code as well as the binary itself. I'm just going to download the binary. I'm not going to really look at the source code. I kind of want to challenge myself to get better at reverse engineering and analyzing code through the disassembly. So let's zoom in. So this is big enough to read, and we can do an ls. I have a flag.txt here. This is just a dummy file that I created, just a proof of concept. We can print it out, and it says please sub. So let's run this vulnerable binary, and it asks us to enter our name. Let's go with Ricardo. And now it's asking us to enter an address to jump to in hex. So we don't know the address of anything, so we can just put this in and we get a segmentation fault. But this isn't a real seg fault where we overwrote the return address or anything like that. There is a structure that is catching our seg fault signal, and it's printing out this custom thing as we saw in the previous video. So let's actually analyze this binary a little bit. We can do a quick check sec to see what mitigations it has enabled. There is a stack canary, and X or dep is enabled, and it is pi. We don't really care about a lot of this. We're not trying to do a return address overwrite or anything like that. We're simply trying to jump to a function. In the first one, there was a win function, so I'd assume this one has a win function as well. There's a million ways we can look at the disassembly or the symbols of this. Let's just do a quick Robin 2 with tac S for symbol and Q for quiet of vuln. And let's grep for imported functions. Or we don't really want imported. Let's grep for, I think this is the syntax. If we scroll through here, let's just not do any grep at all. Let's just print out everything. We should see main. Here we go. We have the address of main. We have address of win. So maybe I would want to do attack V to invert the search. So we have the offset of the win function here. And what else do we have? There's a segfault handler. There's something called call functions. So let's actually open this up in a disassembler. You can use whatever you want. I'm going to be using IDA Pro today. Yes, please analyze it. All right, that was super fast. This binary isn't that large. It spits us out inside of the main function. We see here, if you saw the previous challenge, some of this should look very familiar. We have a segfault handler to catch any segmentation faults. But this is new. We have a function called call underscore functions. So let's double click on that and see what this is all about. We see a familiar string. It's asking us to enter our name. And then it calls fgets, formatted get string. If we just hover over this, it does tell us the function signature. It takes a character buffer, a size, and then a file stream. So knowing the calling convention for x64 on Linux, we know the first parameter will be passed in RDI. So this is the buffer. It goes ahead and it gives it a comment called S. Let's actually just change this to buffer, just so it's a little bit more clear what this is. Let's change this one as well to like number of bytes. I can rename this variable from S to buffer. So how many bytes is it reading? It is doing hex 40. If I hit H on my keyboard, it translates it to decimal. So we're going to be reading up to 64 bytes from standard input. The address of our buffer is being stored inside of RDI. The comment here says it's a format, and then it's being printed out. Okay, interesting. So in the first challenge, when we ran the vuln function from PyTime number 1, it just told us the address of main, and then we could figure out the offset and get the base address of the binary, and then we can calculate the address of the win function, and that's how we solve that level. However, there is no address given to us. We need to somehow figure out how to do it. And I was kind of stumbling and fumbling for a little bit. I was like, okay, so we have a printf here, and we're passing in our buffer. Maybe I can do a buffer overflow, or maybe I can fill up our buffer with junk. So I overwrite some type of null pointer. So when it does a print, it prints out like a library address or some type of stack address or binary address. But that wasn't working. So essentially what we have here is printf with our buffer. So if I open up a quick test.c file, essentially what we have is like call functions, and it's doing printf on our buffer. So this might look fine. This might look good and normal. However, there is a flaw. There's a vulnerability there. Whenever you're just printing out a buffer like that without a format string, like a %s or anything like that, and then our buffer. So we'd want something like this. But instead, what we're doing, and I spelled printf wrong, but it doesn't matter. This is just for sake of explanation. Instead, we have this. So we're just printing out user input. And whenever you notice this or see this, you have what is known as a format string vulnerability. So let's rerun this binary. And I'm just going to throw in some %p's, maybe some %s's, some %x, and we should see that we are going to print out actual data. So what is all this mess? What is this garbage? So all of this is junk that is currently stored on the stack. We see our %p actually prints out some type of hex address. It is kind of hard to read. So when I do these things, I do kind of like to have like a vertical pipe in between just to like separate what's going on. Let's copy and paste a few of these. So now we can start seeing what looks like memory addresses being printed out on the stack. So just like we did last time, we can come over here and we can grab the offset of these different functions and subtract it from here, and we can get the base address of the binary. But which one do we take? Some of these obviously do not look correct. This one might be a stack address. We want something that looks like it'd be the address of main or something like that. We see a lot of addresses that start with hex 55CAB0 and so on and so forth. So these are probably binary addresses. So we could play around and try some of these. But right now, I'm just going to grab this line. Let's quit out of here. And I'm just going to do a little bit more. If I do too much, it looks like we do get a segmentation fault. So we need to find like a sweet spot. But looking around here at the very end, this address kind of sticks out. This looks pretty neat. So what I'm going to do is grab some of these. I don't have an exact number. And let's actually open this up in GDB. We can start disassembling and debugging. Right now, let's just run it without any breakpoints. I didn't get... Let me throw in a few more %p's. I think I need some more. So let's Control C out of here, run the binary. There we go. So I'm very curious about what this address is. Let me just grab this and throw that in here. Make sure this is easy enough to read. And if we look here at our backtrace, it's actually showing us where we just came from. So we're inside the main function somewhere. So if I scroll up a little bit, we see register R8. It says main plus 65. Okay, so let me do a disassemble of main. Remember, this is the address we pasted in. Or where was it? Right here. I'm just going to throw this down here. So this is the address we threw in. And if we look here, this is inside of the main function. And if we go to the very top, we can see where the main address starts. It ends with 5400. And this one ends with 5441. So if we subtract hex 41 from this, we'll get the address of the main function. And then if we take the address of the main function and subtract the offset, which is hex 1400, we should get the binary base address. So here we go. Let's rerun this. Let's slam in the appropriate amount of P's. Let's grab this address, and I'm going to open up a new pane inside of Tmux, and then open up a Python interpreter, and then we can kind of just do some math. So we want to subtract hex 41, and this is to get the main address. Let's throw this inside of the hex function. And then if we take that and we subtract hex 1400 from it, we get the binary base address. So let's come back here to IDA and let's actually find the offset of win, which is hex 136A. So let's add hex 136A to this. Let's grab this, come back to our debugger. So now it's asking us to enter some address to jump to. This should be the address of the win function if we did our math correctly. Let's hit the enter key, and then we see it prints out U1, and then please subscribe. Awesome. So let's do this outside of a debugger. Let's actually make a solve script. I'm going to use pwn tools. So from pwn import all. And let's define some variables here. We can do the main offset hex 1400. The win offset is hex, what was it? 136A. 13, sorry, my microphone's in the way of my keyboard. E equals process, boom. And we want to send this string. With %Ps. So let's come over here. We can say p.send line after. Enter your name. Let's define the name variable. We'll just make it a byte string. And let's read the output. I'm going to save this in a variable, p.readline.decode. And let's print output so we can see what we're working with. I'm going to save this and open up a additional pane and then just quickly run it. So Python 3 solve.py. Oop, I missed this. So I need an asterisk. We're importing everything. Rerun it. Okay, so here's our output. So I use these like vertical pipes to help like denote and separate the output. And we can actually use that in Python here. So I'll show you a neat trick. I'm gonna say output equals output dot split. And we can give it some type of delimiter to split on. So now when we rerun it, everything is in a list. We can see the opening and closing brackets here, and everything has its own elements, and it's a nice, neat string. So we can reference the list with a square bracket. -1 is the last element in the list, and then -2 will be the second to last. let's save and rerun this. And there we go. So this is the address inside of main. So let's, I guess, just rename this. Let's call it inside main. And now we can calculate the main address. This will be a string, so we have to convert it to an integer. So inside main base 16 minus main offset. And let's just print this out. Main address. Ooh, okay. This is a big integer. Let's actually convert this to hex so it's easier to read and understand. Oh, okay. So we need to subtract that hex 41 as well. I forgot about that. So that's the benefit of like printing this stuff out as well as you go. Don't try to write the entire exploit all at once. Kind of just incrementally make changes and print it out and confirm the output and what you're doing. So this is the main address. So now we can get the binary address or the base address of the binary by taking the main address. Forgive me, this is not the main address. This is the base address. Confusing myself. So this should be the base address of the binary. So let's quickly rename this main adder. Let's call it base adder. Main adder. There we go. So this is the base address. So we can get the win address by taking the base address and adding the win offset to it. Sorry, hopefully this makes sense. We can print this out as well. Let's just copy this actually. Win adder. There we go. And it ends with 36A. And if we come back to IDA, we see the offset does end in 36A. So this should be the actual win address. So now we need to actually send this to the function because we'll do vuln and we'll throw in all of this junk, all of this format string, and then it's going to ask us for the proper address to throw in here. So we can do it p.sendLine or sendLine after, either one works, of hex of win adder. Then we want to print the output. So print p.readAll, and this would be a bytes object. So let's decode it. And now we can run it. So it says you won, and then please sub. So let's actually come back to the PicoCTF challenge instance. Let's launch it since it looks like it timed out. And then we can throw in this netcat connection line. So I'm just going to grab this, come back here. Let's comment this out. Now we can say P equals, I believe it's network. No, it's remote. And then throw this in here, throw in this host name, and then the port, which is 52411. Now let's rerun the script, and it tells us PicoCTF Pi shouldn't leak. There we go. So that's actually one of the only ways that I know of, at least, to successfully bypass Pi or ASLR is to somehow get some type of information leak. And that's one reason why binary exploitation is very difficult. If something is compiled with Pi or ASLR, you can't just have a simple buffer overflow. You also need to find some type of information leak as well. So you need to chain together multiple vulnerabilities. So that's why I think it's like a very creative and fun and exciting field. But hopefully this was cool. Hopefully this was interesting. If you guys have any other ways that you've solved this challenge, I would love to know. I was kind of stuck on it for a little bit. And then after looking at it in IDA a little bit, I'm like, oh, wait, maybe there's a format string bug here. Maybe that's something we can utilize. So I'd love to know how you guys solve the challenge in the comments down below. As always, take it easy, and I'll see you in the next video.